So today we're going to be looking at the Alex problem called calculating molality. It feels a little misleading because you're not just doing just molality, you're also doing molarity. And so um, before we get into it, what we're going to have to use to figure this out, like molarity or molality, is these two equations of what they mean, I guess. So molarity is just moles of solute over liters of solution, solution being both a solute and solvent, and then molality being the moles of solute over kilograms of solvent. Now, in this situation, when you read the question, it says the student notices that the volume of the solvent does not change when the methanol dissolves in it. So you don't have to like worry about the change in the liters of solution for this. But for the first part, molarity. So first you want the moles of solute. Now the solute is what they're adding, which is in this case methanol, 4.6 grams. But as you can see, it says moles, not grams. So we're going to convert. And the way we do that is through the molar mass. And so what we're going to do to find the molar mass of methanol is you look at its chemical formula, and then you go to the periodic table and you look at the atomic mass for each one of them and kind of just like add it all together. And then when you do that, you'll get 3204 grams per mole. So if you write out, it's going to look like this. It's going to look 32.04 grams per 1 mole. And since we have 4.6 grams, what we're going to do is you're going to have to switch this to 1 mole, 3204, if that's right. Yep. And then multiply that by 4.6 grams so that when you read it, it cancels each other out. Like this is grams at the bottom, and then it's being multiplied by grams at the top so that they cancel each other out. And then when you do that, you're going to do 4.6 divided by 3204. And this is the number of moles of methanol, essentially. So now that we have the number of moles, we want the liters of solution. Now, it kind of gives it to us, except it's in milliliter format. So what you'll do is you'll do dimensional analysis with this. Essentially, you're going to do 300 divided by 1,000 to get 0.3. Just moves 3 places. So 1, 2, 3. And you could write it out here, but and then once you get that, again, it's moles of solute, which we just found, over liters of solution. And in this case, you don't have to worry about anything weird with that. So you'll do this divided by this. This is the liters. Moles divided by liters. And you get this. Since this is round to 2 significant digits, what we'll do is we'll do 4 and then 7 since this is 8. So we'll put 0.49, capital M. And then this 0 right here doesn't matter. You don't have to worry about this. This is kind of just like a courtesy, I think. And then next we have molality. Molality, so we already have the moles. We just found it this way. Now we want the kilograms of solvent, right? But the difficult thing here is that it didn't give us the grams or kilograms of solvent. It gave us milliliters. So we have to use the density combined with the milliliters to find grams, and then from grams to kilograms to get the molality. So if we look here, it is 0.88 grams per 1 milliliter, and we have milliliter, so we are going to set it up where they cross cancel each other. So we would just multiply by 300 milliliter. And then we do this in our calculator. It's 300 times 0.88. And this gives us the grams, but because you can see right here it says grams, but we want the kilograms, so we'll do this divided by 1,000 because 1,000 grams equals 1 kilogram. So this is the kilograms of the solvent. So now we have this. We already have the moles of solute from before using the molar mass. What we're going to do is we're going to take this and divide it by this. Again, this is the moles of solute, this first number. And the second number is the kilograms of solvent. So you do that, and then you get this number, and it says round to 2 significant digits. So we'll do that. It'll be 0.024, lowercase m, and that's it.